Hello students, welcome to EPG Pathshala. I am Anshul Gupta, lecturer from Delhi Pharmaceutical Science and Research University, Delhi. Today we will discuss module Filtration Technology under Paper Product Development Part 1. In this module, we will be learning about first, principle and mechanism of filtration, second, various type of filtration equipments and their pharmaceutical application. And lastly, we will be studying about filtration optimization process and filter selection. Now, first I will define you what is filtration. Filtration is defined as the process in which particles are separated from a liquid by passing the liquid through a permeable material. The porous filter medium is the permeable material that separates particle from the liquid passing through it and is known as filter. Thus, filtration is a unit process in which a mixture of solids and liquids, the feed or the slurry is forced through a porous medium in which the solids are deposited or entrapped. The solids retained on a filter are known as the residue. The solids form a cake on the surface of the medium and the clarified liquid known as effluent or filtrate is discharged from the filter. If the recovery of the solid is desired, the process is called cake filtration. Now, there is another term called clarification which is part of filtration only. Clarification may be defined as the process that involves the removal or separation of a solid from a liquid or a fluid from another fluid. The fluid here includes both liquid and gases. Clarification can be achieved using either filtration or centrifugation techniques. The term clarification is applied when the solids do not exceed 1% and the filtrate is the primary product. Now we will discuss mechanism of filtration. 4 different mechanisms of filtrations according to the way in which the suspended material is trapped by the filter medium are as follows. First, surface straining. In surface straining, any particle that is larger in size than the pores of the medium deposits on the surface and stays there until it is removed. Particles that are smaller in size than the pores pass quickly through the medium. This is the main operating mechanism for bar screens and the plain woven monofilaments plastic or wire mesh. Filters employing these mechanisms are used where the contaminant level is low and the small volumes need to be filtered. Second mechanism is depth straining. In this, the filter media is relatively thick by comparison with their pore diameters. Particles will travel along the pore until they reach a point where the pore narrows down to a size too small for the particle to go any further, so that it becomes trapped. The third is depth filtration. The path followed by the liquid through a bed is extremely tortuous. The suspended particles are first brought into contact with the pore wall by inertial or hydraulic forces or by Brownian motion. They then become attached to the pore wall or to the another particle already held by the means of van der Waals and other forces, that is entanglement. The particle become entrapped in the depth of the medium even though it is smaller in diameter and possibly much smaller than the pore at that point. Fourth is cake filtration. Cake filtration begins with the formation of layer of a particle on the surface of filter medium with larger pores bridged by a group of smaller particles. The cake acts as the filter medium for subsequent filtration. It is mainly used where solid recovery is the main goal. It can be used for filtration of slurries containing a relatively large amount of suspended solids, usually 3% to 20%. Now we will discuss theory of filtration. The flow of a liquid through a filter follows the basic rules that govern flow of any liquid through a medium offering resistance. The rate of flow may be expressed as rate is equal to driving force divided by the resistance. The rate of filtration is given by modified Poiseuille's equation as shown on the screen. Here, V stands for volume of filtrate, T is time, A is the filter area, P is total pressure drop through the cake and filter medium, micro is filtrate viscosity, alpha stands for average specific cake resistance, W is the weight of dry cake solids, R is the resistance of filter medium and filter. The rate of filtration is also given by Cosny equation, which takes into account the resistance offered by the filter bed. You can see the equation on the screen. The rate of filtration is also given by Darcy's equation, which takes into account irregular and non-uniform capillaries formed in the filtration bed. The Darcy equation is like that which is shown on your screen. In this, K is the permeability coefficient and depends on the nature of the precipitate to be filtered and the filter medium itself. Now we will discuss about filter media. Filter media is the surface upon which solids are deposited in a filter. Now some of the characteristics of filter media are: first, they must retain solids without plugging and without excessive bleeding of particles. Second, they should offer minimum resistance. Third, filter media should be chemically and physically inert. Fourth, it should not swell when it is in contact with filtrate and the washing liquid. It should have sufficient mechanical strength to withstand the pressure drop and mechanical stress during filtration. And lastly, it should allow easy discharge of the cake. Different types of filter media are: first, filter cloth like cotton, nylon, Teflon. Second, woven wire cloth like stainless steel meshwork. Third, non-woven filter media like felts, bonded fabric, craft papers, etc. Membrane filter media are thin membranes about 150 micron thick and with 400 to 500 million pores per centimeter square of filter surface. These are mainly classified as surface or screen filters and are made up of various esters of cellulose or from nylon, Teflon, polyvinyl chloride, polyamides, polysulfone or silver. Now we will discuss filter aids. Now during normal filtration, a solid, thick and impermeable cake is formed which offer resistance leading to a low filtration rate. Filter aids are a special type of filter medium. The filter aid forms a fine surface deposit. They form a highly porous and non-compressible cake that retains solids, so offer less resistance to the flow of filtrate, increasing the rate of filtration. The important characteristics of filter aids are: first, they should form a pervious cake. Second, they should remain suspended in the liquid. Third, they should be free of impurities. Fourth, they should be inert to the liquid being filtered. And fifth, they should be free from moisture in cases where the addition of moisture would be undesirable. The table shown on the screen shows various filter aids with their advantages and disadvantages. Now we will discuss filtration equipments. Commercial filtration equipment is classified by end product desired, that is filtrate of cake solids, by the method of operating, batch or continuous, by type of operation, non-sterile filtration, sterile filtration, centrifugation filtration, centrifugation sedimentation. But most importantly, by type of driving force, that is gravity, vacuum, pressure and centrifugation, as it can be shown on the screen. First, gravity based filters. These are sand, candle type, tray and frame, gravity bag, gravity nutch. Second is vacuum based, rotary drum, disc type, horizontal belt, tilting pan and nutch type. Third is on the basis of pressure. Example, filler leaf, sweet land and filter press. Fourth is centrifugation based, for example, perforated basket type. Lastly, centrifugation sedimentation based, for example, tubular bowl, conical disc and horizontal continuous type. Now first come to gravity filters. Gravity filters rely on the gravity generated low operating pressure and give low filtration rates. However, these are simple and cheap and are frequently used in laboratory filtration where volumes are small and low filtration rate is relatively insignificant. Now secondly come to vacuum filters. These are employed on a large scale but are rarely used for the collection of crystalline precipitates or sterile filtration. Vacuum filters are simple and reliable machines and therefore have gained wide acceptance in the chemical, food and pharmaceutical industries. Under this, we will discuss rotary drum filter. The rotary drum vacuum filter divided into sections, each connected to a discharge head. Each filter unit is rectangular in shape with a curved profile so that a number can be joined up to form a drum. Each unit has a perforated metal surface to the upper part of the drum and is covered with filter cloth. The slurry is filled to a tank in which solids are held in suspension by an agitator. As the drum rotates, each section passes through the slurry and vacuum draws filtrate through a filter medium at the drum surface, that is pickup zone. The suspended solids deposit on the filter drum as a cake, and as rotation continues, the vacuum holds the cake at the drum surface. For solids that tend to block the filter cloth, a pre-coat of filter A such as diatomaceous earth, perlite and cellulose is deposited on the drum prior to the filtration process. These materials serve as a filter medium in an analogy to the filter cloth on a conventional drum filter. Now come to plate and frame filter press. The plate and frame filter press is the simplest of all pressure filter and is most widely used. The filter presses are used for a high degree of clarification of the fluid and for the harvesting of the cake. As the name implies, the plate and frame filter press is an assembly of hollow frames and solid plates that support filter media. When assembled alternately into a horizontal or a vertical unit, conduits permit flow of the slurry into the frames and through the media. One side of the plate is designed for the flow of the feed. After passing the filter media, the filtrate is accommodated on the other side. The solids collect in the frame and the filtrate is removed through the place conduits. In cake filtration, the size of the frame space is critical and wide sludge frames are used. Its advantages are: it is simplest and most versatile press. It can be used from coarse to the fine filtration. It can be used for multi-stage filtration within a single press, and lastly, most economical filter per unit of filtering surface. However, some of the disadvantages are high labor cost in the assembly and cleaning of the press. Secondly, leakage between plates may occur through faulty assembly. Now come to the topic centrifugation, filtration and sedimentation. Centrifugal force affects the passage of liquid through the filter medium. Filtering centrifuges are used for filtration of very fine particles and where solid recovery is the prime goal. Whereas centrifugal sedimentors is used for complete separation of solid liquid mixture and liquid liquid mixture. Residual moisture in cakes after filtering centrifuges is far less as produced by pressure or vacuum filtration. It is as low as 3%, so it facilitates the drying operation. Filtering centrifuges is widely used for separating granular products from liquors, but it is less effective for concentrated slurries containing smaller particles. Perforated basket as shown on the screen. It consists of a perforated metal basket mounted on a vertical axis by means of which it can be rotated at a speed of 20 to 25 revolutions per second. The cloth used to retain solid is often supported on a metal screen and the outer casing collects the liquid thrown out from the perforated basket by centrifugal force. The baskets mounted are emptied by shoveling the cake. In batch operation, considerable time is lost during the machine acceleration and deacceleration. Machines operating with continuous discharge of solids are used for separating coarse solid during the large-scale operations. Such machines are commonly constructed with a horizontal axis of rotation. Now, centrifugal sedimentors. Rate of settling of particles in a liquid is described by Stokes equation as shown on the screen. In the centrifuge, the gravitational force causing separation is replaced by a centrifugal force. So, the equation now becomes as shown on your screen. Equating the two expressions, we will get rate of settling of particle as a function of radius and speed of basket as again shown on the screen. Thus, we can conclude that the sedimentation rate is proportional to the radius of the basket and the square of the speed at which it rotates. Centrifugal sedimentors can be divided into various types. For operation at a very high speed, the centrifuge bowl is tubular with a length diameter ratio from 4 to 8. An example of tubular bowl centrifuge is the sharpless supercentrifuge as shown on the screen, which operates at up to 15,000 rpm, or in turbine driven laboratory model up to 50,000 rpm. The machine is an effective clarifier when the concentration of solid is very low. It also gives continuous discharge of two separated liquids and is widely used in emulsion separation. Some important uses include cleaning fat and waxes, blood fractionation and virus recovery. The other examples are conical disc type centrifuges. It is also shown on your screen. It consists of series of conical discs into the bowl. Its length to diameter ratio is small and operational speed is low. Now coming to its working, as the centrifuge rotates, the heavier liquid or solid moves underside and the lighter liquid moves to the upper side of the disc. It is used for separating lower concentration of solid. Another example is horizontal continuous centrifuge. It is also shown on your screen. It can handle solids with wide particle size range and in slurries with concentration ranging from 0.5 to 50%. Now we will discuss specialized filtration. One such filtration is sterile or aseptic filtration. The old and the traditional way is by the use of asbestos pad, unglazed porcelain candles. It has limitations like it is fragile, cleaning is a problem, chemical pre-wash and pH adjustment sometimes become troublesome. Now at present we are using membrane filters. At present membrane filters have become a basic tool in sterile filtration. They have been officially approved by USP and US FDA. For membrane filters, no pre-treatment is required. They can be sterilized by autoclave or can be gas sterilized. The recommended porosity of membrane filter is 0.2 or 0.45 micron for sterile filtration. For example, simple formulations such as intravenous solution, ophthalmics and other aqueous product may be filtered directly through these membrane filters. However, heat labile oils and liquid containing proteins require pre-treatment, example centrifugation or conventional filtration prior to sterilizing filtration. Now come to the membrane ultrafiltration. Ultrafiltration is a process of selective molecular separation. The difference between microfiltration and ultrafiltration is that microfiltration removes particulates and bacteria, whereas ultrafiltration separates molecules. Its working principle is similar to the principle of reverse osmosis, as both filter on the basis of molecular size. Dialysis and ultrafiltration are similar in the sense that both process separate molecule, but is different in that it does involve application of pressure. The configuration of molecule and its electric charge may also affect the separation properties of membrane. Ultrafiltration membranes are available as flat sheets, plated cartridges or hollow fibers. The hollow fibers have selective skin on inside of fiber. It is used to recover antibiotics, hormones or vitamins cell from fermentation broth. The most important application of ultrafiltration is the removal of pyrogen. Now comes to the optimization part, filtration process optimization. Here we will first discuss pre-filter optimization. The optimum system often requires use of a series of filters in a single multi-layered filter containing layers of various pore sizes or a pre-filter followed by a final filter. Optimum performance is obtained when the filters in a series exhaust their dirt holding capacities at the same time. When the flow resistance across each filter in the series approaches the limiting pressure drop, the dirt holding capacity of the system is considered expended. Figure from A to D as shown on the screen shows the pre-filters with adequate and inadequate dirt holding capacity. In the figure B shown on the screen, the coarse pre-filter does not provide sufficient retention efficiency, thus causing the poorly protected final filters to clog prematurely. Too fine a filter on the other hand has enough retention efficiency but insufficient dirt holding capacity, and it plugs very quickly as shown in the figure C on your screen. Now figure D, both filter, the final filter and the correct pre-filter will have almost expended their dirt holding capacities as the last of the batch is filtered. A final filter that is not protected by pre-filter has a short filter life. When a pre-filter is used in combination with a final filter, the efficiency of the pre-filter is maximum, and these cases it is important that the O-ring seal sits directly on the membrane itself and not on the pre-filter. Therefore, the diameter of this pre-filter selected should be somewhat smaller than the diameter of the final filter. Seating the O-ring on the pre-filter often fails to produce a seal, thus causing the filtration system to leak. This leakage may result in the filtrate being exposed to the contamination. Now, filter media optimization. A nephelometer is an excellent tool for assessing the effectiveness of the filter media. A nephelometer is an instrument that measures the degree of light scattering, that is Tyndall effect, in the dilute suspension, and thus help in measuring the particle size range that has come into the filtrate after filtration. Most pharmaceutical filtrations aim for the removal of particles of 3 to 5 micrometer or less, which can be assessed by use of nephelometer by determining particle size in the filtrate. The nephelometer gives a quantitative value to the formulator's quality specification of sparkling clear. This value may be used to compare results using different filtration media and thus allowing to choose the best to suit the need. Now comes to the filter aid optimization. As the filter aid concentration increases, the flow rate increases and peaks off. Beyond an optimum quantity, the flow rate decreases as the filter rate concentration is increased, as depicted in the graph which is being shown on your screen. Filtration cycle optimization. The question of time for a filtration cycle is resolved by determining total volume versus time during a test run at pressures approximating normal operating condition. Flow rate decreases with the time as the media plugs or as the cake builds up. Plotting log total volume per unit area versus log time usually give a straight line suitable for limited extrapolation, as shown in the figure on your screen. In semi-continuous operation, decisions must be made on the length of the cycle prior to the shutdown for replacement of media. If the goal is maximum output from the filter per unit of overall time, the graphic approach of the figure is applicable. During productive time T, the filter discharges a clear filtrate at a steadily decreasing rate. Non-productive time T prime is required to clean the filter and replace media. For graphic analysis, non-productive time T prime is plotted to the left of the origin of a volume V versus time curve. When a line is drawn from T prime tangent to the curve, the value of V and T at the point of tangency indicates where the filtration should be stopped. The time lost in cleaning is offset by a return of high filtration rates associated with the new media. This point also can be calculated from the theoretical relationships for constant pressure or constant volume filtration. Data from lab equipments can be applied to the production units since the analysis is independent of filter area. Lastly, we will discuss about how to select a filter. In designing or selecting a system for filtration, the specific requirements of the filtration problem must be defined. The following questions should be answered before any assistance is required from the manufacturers of filtration equipment. First, what is to be filtered, liquid or gas? What liquid or gas is to be filtered? What is the pore size required to remove the smallest particle? What is the desired flow rate? What will be the operating pressure? What are the inlet and outlet plumbing connections? What is the operating temperature? Can the liquid to be filtered withstand the special temperature required? What is the intended process, clarification or filtration? Will the process be a sterilizing filtration? Will the process be a continuous or a batch filtration? What is the volume to be filtered? And lastly, what time constraint will be imposed, if any? So, considering all these questions will help you in selecting filtration media and equipment accordingly. Thus, to conclude, in this model we have learned how an industrial pharmacist can achieve a balance between filter media, equipment capabilities, slurry characteristics and quality specification for achieving desired final product. Thank you, students.